The entire system is implemented on the cloud. We use the AWS IoT Core Service, which provides an MQTT broker to which messages can be delivered to or read from. As you can see, this is the MQTT client which has been configured, and here we are able to publish and subscribe to any topic of our choice. By using the AWS IoT Core Service, we have been able to achieve little to no latency, which is extremely crucial, especially in medical applications such as ours. Coming to the Arduino IDE, this is the code that is directly flashed onto the microcontroller. For an authenticated connection with the corresponding AWS account, we have generated and used certificates which have been appropriately converted to their formats, which can be read by the microcontroller using OpenSSL. For this to work for the MQTT broker to work with the Android application, we use the AWS Cognito service in place of this. This is the code, as you can see. The data generated real time from the microcontroller is also stored in real time in a NoSQL database called DynamoDB so that the data can further be used for analysis and processing, which could be a crucial part in the upcoming modules of our project.
Okay, coming to our app. When you open the app for the first time, you're presented with two choices, whether you're the person controlling the ventilator or whether you're the companion for the ventilator itself. So I'll explain both of them in detail as we go on. So let's start with the ventilator first. When you click on it, you're prompted to enter the patient name of the person who's currently being ventilated. So let's say I enter my name and it feeds it into our database. I'll tell you why this is relevant later on. So it takes you to the next screen wherein the person who's helping ventilate the patient is presented with a couple of graphs as well as a button that starts and stops the ventilator. So as soon as I click start, it starts connecting to the AWS IoT Core service and reads data from the heart rate monitor and the pulse oximeter. So as you can see, as soon as I click start, the values that are obtained are instantaneous, and these are real-time data that are obtained from the IoT Core service. This is also the button responsible to start and stop the ventilator. So if you want to control various parameters that the ventilator can have, such as how much air to provide or how fast it should go, you swipe up from the bottom. And this gives you a screen to control total volume and respiratory rate that's measured in breaths per minute. So these are slider values and you can fine tune them to as much as you can. So in our ventilator, we have limited it to 1100, which is the maximum capacity of our ambu bag. Similarly, you can also change the respiratory rate, and that's measured in breaths per minute. You also see a button that's called Connect to Base. So this is where the companion application comes into place. So when the companion application registers, you get an ID. And when I click Connect to Base, I'm prompted to enter that ID. So I know the ID of my companion is 13, and I click on Connect. So then as soon as it's connected, I get a notification saying it's connected, and it's also reflected in the companion application. So what this essentially does is that the companion application can now remotely monitor the status of the patient as well as the ventilator, and also will be alerted if in any case the ventilator fails. So that's one of our fail-safe mechanisms. So now I'll go on to the companion application to explain further as to what are the functionalities of that. Okay, so this time around we'll log in as a companion. So when you click on companion, it'll prompt you to enter your hospital name. So for our case, I'll just put tester. And click on done, it'll log you in and take you to the next screen. So over here you see Achuth, the person that we just connected the base to, as well as a green tick. That means it's available and working without any issues. And if you want to monitor his or her vitals, it's just one tap away with the same screens, except now you can't start and stop because that would be an operation performed by the person who's controlling the ventilator itself. So now we'll see what happens in the off chance that the ventilator that's used for Achuth loses connection. So I've switched off the ventilator that's connected to Achuth, and as you see, as I'm speaking, it'll come as ventilator for Achuth has malfunctioned, as well as a red um, indicator that says something's wrong. And as soon as you tend to it, and as soon as the issue is fixed, it'll turn back to green to indicate that the ventilator is indeed working. In addition to the companion, it also creates a loud alarm that sounds both on the ventilating application as well as the companion. So it'll alert you even if you're not actively looking at the application to monitor any such discrepancies. And that's how we ensure fail-safe measures are followed throughout the application.
Okay, now let's talk about the hardware side of the project. To begin with, the goal here is to compress the ambibag at variable frequencies and displacements. The mechanical setup is something that we built upon scrap materials that we could find and recycle from things around the household. We're using the NEMA 17 stepper motor that delivers a maximum torque of 4.2 kg centimeter, driven by the A4988 stepper motor driver module and a 12 volt 2 amps power supply. The microcontroller used is the Node MCU with ESP8266 at heart. We're also using an Arduino Nano to offboard some of the computation from the node, which will communicate over serial. We're also using the MAX 30100 pulse oximetry sensor for SpO2 and heart rate, and a 3-axis accelerometer and gyroscope to track the patient's diaphragmatic movement to analyze his or her respiratory pattern. An additional buzzer is added to the circuit to give a feedback for every detected heartbeat. Well, that pretty much sums up the hardware components. Now let's look at how everything falls into place, including the Android app, which is opened up here, and also the MQTT cloud architecture working in the background. As you can see, I am already a registered user and is currently in the ventilator mode. Now, when I press the start button, you can notice how quickly it reflects on the hardware. Now, it begins the process of resuscitation almost immediately. Similarly, I can stop the process from the app itself. Right after one of the cycle finishes, it immediately stops. Now, when I go into the settings and change one of these parameters, let's say the total volume that is delivered, to half of the actual value, we can go back and see what happens when we start it again. As you can see, instead of going all the way down to compress the entire bag, it's only going halfway down because we specified we need only half the volume output. Let's stop it again. As you've already noticed, the parameters changed from the Android apps interface reflects almost immediately on the hardware side. Now, this is because both the Android app and the entire hardware setup subscribes and publishes to two different topics hosted on the AWS IoT Core MQTT broker and communicates over it. There is almost no latency involved here, and any such problems introduced at any point of time in future will also again be solved effortlessly by the fail-safe mechanisms we've implemented for the worst case scenarios. Thank you for your time, and I hope you have a very healthy day ahead.